Welcome and thank you for joining us. My name is Lisa Aguirre and I'm the product manager here at Roland DGA, DG Shape Americas. Today we're thrilled to have Kris Schermerhorn CDT, and owner of Northern Virginia Dental Laboratory, here to tell us a little bit about digital denture milling made fast and simplified. He'll explore tips and tricks on how to integrate a simple removable digital denture workflow into your lab, fast and easy with profitability. Before we begin, we do ask that you please save all questions for the live Q&A session at the end of the presentation. So let's get started. Kris?
Great. Thanks, Lisa. Yeah, so what we're going to talk about today is taking you through that process of producing an appliance with your software and mill. We're going to talk about design, nesting, which is positioning, placing whatever you've designed into a puck to go into whatever mill you might be using, milling it, and then finishing and polishing it. Kind of take you through that whole process. First thing you want to do is actually create the, whatever you're going to be milling. We're going to go through, of course, acrylic and producing a denture. We're going to talk about partials as well, being able to use some other unique materials other than acrylic. We're going to talk about bite splints. Really kind of give you a full idea of exactly what can be produced out of a mill. A lot of people don't realize that, they purchase a mill that is expensive, but, if you can keep that mill working, it's going to earn its keep. It's like an employee, and the employee you don't want sitting twiddling their thumbs because they don't have work to do. You don't want that mill sitting idle either, or rather run that mill into the ground than to see it sitting there idle. Bought a boat, and the one thing I said with the boat was I told my father he could use the boat at any time. I told my father-in-law, use the boat anytime. I'd rather run that boat into the ground and have to buy another one than to let it sit there and deteriorate, right? So we're going to make sure that you have a good idea of what you can actually accomplish with that expensive mill. Let it earn its keep. So we're going to talk about design with 3Shape as well as CAD. They're kind of your two major design softwares that I have experience with that are really nice software to use. There's some others out there that I don't really have direct contact with, but they're all really stepping up, all the different companies with their technology and design. I'm going to talk about kind of frameworks, and I'm going to go side by side with 3Shape and CAD here. Just give you an idea how their workflows differ a little bit, and it's not that different. That's the cool thing. If you had 3Shape and were fairly proficient with 3Shape, you could jump over to CAD and just in a short period of time kind of adjust to the slight differences and be rolling right along. Vice versa. The software. Those companies, they're not dumb, by any means, right? And they, if something works, they're going to generally probably be very similar because if it works, it works. So CAD, the first thing that's going to do is block out. And that's really a nice thing especially with flexible type partials. So it's always been a bit of guesswork in our industry dealing with the undercuts when it comes to flexibles, because with parts and parcel, it moves and flexes, and it's hard to predict how much it's going to be able to flex and be able to block out. Well, the software kind of gives you that, establishes the path of insertion, and that's really important for making sure that these partials come in and out of the mouth smoothly but still retain. And so it'll give you a degree of undercut. Red will be an extreme undercut, kind of transitioning to orange to yellow to a green to a blue being your lightest undercut. And so you can kind of choose to expose what you want to expose. With most flexibles, the tip of the clasp a lot of times can go into the red undercut. Now, red can be a few degrees in an undercut. Red could be, a crazy amount of undercut So I would say, especially at the start, if you have a little experience, keep the tip of your clasp into the orange. Don't really venture into the red. And then as you get some experience, get some cases, you could run a tip of the clasp into the red, knowing that you may have the ability to trim it short if it is too extreme and it not affect the design or the fit of the case. It's a good way to kind of experiment, see where you can get to and how far you can go with things. Because it truly is still, even with the software, comes with a little bit of experience. 3-shape, similar, right? A deep red, lighter red, lighter, even red, and then transitioning to like an orange to a yellow shows you the undercut. So same thing, and this one's kind of we're going to have the clasp coming across here. You wouldn't want the base of your clasp coming across a red for sure, right? No matter what, because that clasp is going to roll into the body of the partial or into acrylic, depending on what your design is and what kind of partial you're creating. Well, the clasp is going to cease to be flexible right here as it goes into that acrylic. So I don't care if it's flexible or not, it's not going to be flexible right there. So you definitely want to stay above the height of contour and then go into a deeper undercut with the tip of the clasp. Tip of the clasp can go into really extreme undercuts. Base of the clasp, you avoid that. Really block that out and have your clasp come across the top of it. Jumping back to ExaCAD, what ExaCAD has you do is mark, and then we're doing like a framework type design here. So we're going to have mesh, very similar to a metal framework, except for we're going to make it out of either a acetyl resin or a Duraflex VisiClear type of material, Dentavera type, whatever can mill. There's I think Thermozen it's called, or something that has a puck that's a nylon, whatever it is. If it's a flexible partial and you're going to be milling it, this is the type design I'm doing. It's going to have internal extra finish line, mesh work, and then you're going to process your acrylic to it, regular pink acrylic and denture teeth. The advantage to this is you get all the flexibility and comfort and aesthetics, but you still have acrylic on the saddle, so you could do relines and repairs easily. So ExaCAD has you mark the block out for your mesh. Nice large tissue stop. We want to have a nice large robust tissue stop because it's flexible. We want to keep it stable. And it'll have you mark to that your major connector. Now you can also choose to mark your clasp as part of your major connector if it's more of a wing type clasp. Or you can put it on secondarily. The software will prompt you to add a clasp, and you'll do a spline. Click your dots along the path that you want that clasp to be, and do it that way. I opt a lot of times to just kind of carry my major connector and make it part of it. Saves a little time, and generally the thicknesses you'll have to smooth it down a little bit, but it'll be right about where you need to be. With materials like acetyl, they allow for they're a little stiffer, not quite like a Valplast or a TCS type material where it's super flexible. So you can rest as long as it's a substantial rest. It can't be a little teeny thin rest, but you can rest with it if it's thicker. 3-shape, it has you mark your mesh and then accept your mesh and then mark your major connector. So very similar, just one is asking to accept one before it goes on to the other. The other one's having you mark 2 before it goes on. So again, very similar, just slight differences. And here's how your partial will turn out, right? So this is it without finish lines, right? So my finish lines are here. So basically when you mark your mesh and mark your major connector, this is what will come up. You'll have to smooth a little bit. I find with ExaCAD, you have to do a little more smoothing. 3-shape. When it accepts things, tends to smooth things, the joints between the different parts that you've created a little bit better. Seems to be just a bit faster that way. On the other hand, ExaCAD does allow you to kind of arbitrarily add material where and whenever you want. Whereas 3-shape, you have to kind of create a spline and then create parameters around that spline, and then once you save it, you can make it fatter and thicker, and you can smooth what's there, but you can't really add to the contact area. You can't add beyond what was originally created. Now you can do little workarounds like create a secondary spline and tell it it's a clasp or something and have it put it on there and then smooth it in. You could definitely do some tricky things to kind of get around that. But you know, all these softwares are great. All of them have their pros and cons. I'll just give you a little my insight into the differences. So you smooth this, then you'll do a spline and add your finish line. Do you like to have that finish line a little robust and a little bit, you know, heavier than you would for metal? Your major connector generally is going to be, you know, defaults around 7/10. That would be for metal. This is not metal, right? So they are going to be a little heavier. Probably going to be about 1.2, 1.3 for most cases in the major connector. Your blockout is going to, you know, the actual blockout under the mesh defaults usually around 6 to 7/10. This is going to be at about 1 millimeter, and the mesh itself is going to be about 1 millimeter. So, you know, all of it's definitely thicker than metal. Metal's strong stuff. It can be, you know, thin and dainty. But a lot of patients, they'll have metal partials for years, switch over to one of these, and they kind of go, man, it feels lighter. Feels actually lighter than my metal. You know, and it is. It's lighter in weight, but it's actually not thinner, but it feels thinner to them. So it's interesting, you know, how that is. 3-shape, again, spline, create your finish line. Cool thing 3-shape has is you can click on each individual spline point, and you can hold your shift and or your control or both and affect the width and or the height of that by just rolling your mouse button. So that's kind of a cool little thing with CAD. You have to kind of go into the setting. It's a little button, you click, setting comes up, and then you just kind of click on the size, like to make it taller or broader. So you can do both. It's just 3-shape's little, you know, hotkey is a nice little addition, little quick thing to make it broader. And again, I like also 3-shape's little undercut that they add to that. It helps to lock things in. And so you can see here, designs are similar. Process is somewhat similar, you know, it goes pretty smooth, but just the little differences between them. Again, the different materials. Acetal, for people that don't know, is a semi-flexible, highly crystalline thermoplastic. Comes in tooth colors as well as a pink. Can be used in a lot of different situations, even other than partials, and we'll talk about that in a little bit. It's a pretty cool material. The VisiClear, that is a mostly clear, not crystal clear, but mostly clear plastic, very flexible, and it was real nice for frameworks, even bite splints. Wouldn't be super wear resistant, but definitely would be comfortable. And it'd probably be about as wear resistant as regular acrylic. Then we have Duraflex. The Duraflex is basically VisiClear, same material, just with a pink pigment. So everything I talked about, that goes for each. And then the Dentavera, that's even stiffer than an acetal type material. It comes in 2 different kind of tooth colors. One's kind of a white, like maybe an A1 or a B1, kind of bone looking, very opaque kind of look. Or it comes in what they call like a tan, I think. And that is probably like an A2 or A3, I guess. It's one thing that's nice about this material is acrylic will adhere to it. These materials, acrylic will not bond to it. So we'll talk about them a little bit as we go along. So, you know, in a mill, you have, with like an acetal material, the ability to create a good variety of things. And the big reason I'm showing this is, you know, again, you know, I'm a lab owner, and when you spend a substantial amount of money on something, again, you want to keep it busy. And so here's a good example of a framework, right? And this framework, you know, to have acrylic saddles on it, processed teeth, unilateral, same thing, it's prepared for acrylic and teeth. This is a long-term temporary, so the acetal can, you know, comes in all the, Comes in a bleaching shade B1, A1, A2, A3, A3.5, and then a C2 or C3, I think it is. So it has a variety of tooth shades, and when the material becomes you know, a little thicker, like major connectors, a little bit more than a millimeter, so it'll has some flex to it. There's no real area for the most part that's below probably 2 or 3 millimeters, and it becomes substantially more rigid. I mean, pretty much as rigid as any acrylic. Acetyl resin doesn't absorb any moisture, and so, you know, it is really, and it's super tough, right? You know, you're looking at 8 to 10 times, depending, you know, it kind of has its strength in a different way from PMMA, but, you know, it's much stronger than a PMMA, and it doesn't absorb any moisture either. So if you're sealing a margin with a temporary, it's going to be in there for an extended period of time. It's really going to protect that tooth. So it's really nice for a long-term temporary. And then a bite splint. The material is very wear resistant, really does a good job there. And so I have a few doctors that'll do these regularly, and because of the toughness. Very biocompatible. So patients have any allergies, it works really nice. Doesn't come in a clear, so you want to make sure your doctors understand that. Also, what I would recommend is to process it in a bleaching shade. The bleaching shade's nice and white, and so I think because it doesn't clear, you don't want to like get a tooth color and make, you know, if they're A3 and I have this big chunk of A3 in the mouth. You want it to be nice and white, it looks clean, and I think patients are more accepting of it if it's like that. Pink, so this is a pink frame. This is out of an acetyl. So the pink's nice. It's not as pretty as like a Valplast or a TCS as far as the clasps, right? Because it doesn't have the translucent. This material, acetyl resin, is a highly crystalline, so it doesn't have translucency to it. It's pretty opaque. So definitely like a Duraflex or a Valplast or a TCS is going to have more translucency and blend in a little better. But if you design your clasp right down at the neck of the tooth, the patient doesn't have a huge high smile, probably going to be fine. You know, I don't know, a lot of the percent of time. I don't give a number because it's really hard to predict that. But you just want to research, try to clasp in the posterior. But I like the pink. Some doctors will have a hard time, and patients will have a hard time with the tooth colored major connector, right? So you could do a tooth color clasp, but the problem is then the major connector is tooth color. You could process a clear clasp to these frames, locking them on mechanically, but now you're talking about so many levels of steps, the cost is going to go up, and you know, it can be problematic. So those are some options there. The Dentavera Solvay material, this is that bone colored stuff. I have a doctor that does bite positioning and tongue positioning appliances, and he loves the fact that it's strong. He loves the fact that it's biocompatible and that it doesn't absorb moisture and it stays real clean. And he would love that about acetyl, or he'd love it about VisiClear, any of those others, because they all have very similar properties in that. The one thing is he a lot of times will need to add to this material, and acrylics will 100% bond to this material. Matter of fact, I milled this, I did a test. If you can see the remnants here, this was a block of acrylic that I bonded on, and I actually hit on it with a hammer probably 3 or 4 times, finally gave it a good whack, and you can see this is the pink acrylic. It actually split the block and snapped itself off. So it bonds as good as I've ever seen anything bond even to acrylic to itself. So really good example there of kind of a cool appliance, and how these materials can be used. And hopefully your minds are starting to think, oh, I really did want a material like that, but I did need to add to it. It's nice if you have to do a partial and maybe you want to do veneers like denture teeth or build up composite or something like that to it. You don't have to worry about creating, like on chrome, creating some sort of mechanical keyway or lock for the veneer tooth to kind of adhere to. And then they still wind up getting popped off if you don't, you know, if the patient comes up over and hits that incisal edge. This is nice because it will bond 100%. And because it's tooth color, at least generally close to a tooth color, you don't have to really opaque anything. You know, sometimes you get that gray metal when you cut a denture tooth down so thin that all of a sudden affects the actual shade of the tooth. So you don't have to worry about that. So it has really cool uses. You can even, because it has a stiffer properties to it, metal strengtheners inside dentures. This is a bar. Now this is a little iffy. The interface is metal. There's a tie base in there. There's a little fogginess on whether this would be FDA, approved or not, because the interface is metal, but it is something, and they do say it needs to be removable from the mouth. Well, this is by screws. So that's all kind of up to you, and Fuzzy, you can decide how you feel about that. VisiClear and Duraflex, again, they're both the same thing, right? So anytime you hear anything about one or the other, they are the same material, just one has pink pigment to it. So that's a little overview of some unique things, unique materials that you could create with your software and also mill with your mill. Jump into acrylic and jump into dentures a little bit, right? So there's a lot of different companies that have different ways of going about creating a denture. It's a little bit new, whether you're 3D printing or milling, it's all a little bit new. And so people really have a good variety of ways of producing a digital denture. Over here we have Ivoclear, kind of cool. You mill your base partially. You have your teeth printed, I think milled with theirs, and I'm not an expert on theirs, so forgive me if I'm wrong, but I believe process is to mill the teeth, mill the base partially, glue your teeth down in place with they have a resin or some sort of a bonding system. It's supposed to be real good. Of course, when you push it down, you're going to have oozing of material and stuff, but then you put it back in the mill and it goes back over and cleans up that residue and finishes milling the denture. Kind of a cool idea. Roland has a really cool thing. It's a kit where you can actually make your own pucks. So there's an expense savings, depending on how you look at it, right? So you have probably pennies or maybe $1 in material costs. You have a little labor, but it's really easy. It's just a little rubber mold. You fill it with your acrylic. Really thought there was going to be issues with bubbles. They have a few acrylics they recommend. I've also used a few other companies' acrylics that have worked fine. When I was, my father started the lab back in the 60s, so I was in the lab really early, cleaning it and doing a little model work. And so I would say in '93, I was actually in the lab pretty well full time. And I remember back then, there was always a challenge with processing dentures. If they were a little thick, you get bubbles. But nowadays, the acrylics have gotten so better. So when I saw this kit, I was like, oh, we're going to have a heck of a time with bubbles. But it doesn't seem to be that big of an issue. Every once in a while, you'll have something on, but usually just on the surface, and it doesn't matter anyways. But yeah, it's a cool little kit where you create your own puck, right? They have a special holding bracket for the puck you create. And then you'll mill your denture, and then you can decide, however you design it, 3Shape, CAD, or whatever, every other software you might use, mill, print your teeth, and then bring them together. You can bond however you would choose to bond. We'll talk about bonding here in just a little bit. So really a pretty cool system there. So yeah, you can see here, this is a good example of partially mills, but the sockets are fully milled. And then you mill your teeth, set them in, again, glue them, and then it goes back and finishes that job and mills the excess. So kind of a cool option. Abutment, they've been doing this a good long time. Most of their stuff is in-house, design. I think they'll take your design. Again, not exactly an expert with theirs, but just want to make sure you guys have a full array of the ways of producing digital dentures when it comes to milling. So yeah, pretty cool process. So we've gone through design, we've gone through some unique ways of producing. Once you create that and you want to nest it, just a couple little things. The first thing I will recommend is With dentures, with a bite splint, with whatever it might be, when you get it positioned in the puck, turn the puck so that you can see down into your denture or whatever it might be. And it'll show you undercuts. Now you can kind of see it here. It'll show you an area where it's worried by kind of discoloring it. So you have these arrows where you can turn and twist your appliance in the puck. So what I would do is just turn your appliances so you get rid of as much of that as possible. Now your mill, you know, a roll-in mill will have, you know, it's 5 axis, so it's going to be able to reach a lot of these undercuts. But you just want to help it out a little bit by positioning in there, especially a denture. If you have a ridge, you know, you can kind of, usually it's up in the anterior, right? So if you could tilt it so that tool can get up in that anterior, because usually back in the posterior, there's not much going on. There's not much it's going to have to fight against. So it'd be really more of the thickness of the puck, so you could tilt it inside there and still not, you know, get it too wide for the broadness of the puck. Also, if you look here, you know, they're showing you this to say, oh, don't have this. I've found that if, and again, this is this is at your own risk, but if you scoot this to the edge so that you see this, but it's not connected, that means it's protruding just into the border. But believe me, if you scoot him in and get a little of that, whenever you have 2 things that are fitting extremely tight, you can get away with that. So again, that's at your own risk. That's a warning, but as long as it's not attached, like you'll see this clarity through here, you're going to be fine. So yeah, there's our undercuts that you want to watch out for, and you want to try to position. These are somewhat minor, so we'll be okay. When you mill, right? So plastics, we've been doing this somewhat recent and relative to zirconia and crowns and stuff like that. So they're now really developing some nice strategies and tooling to be able to, you know, mill these faster. You know, zirconia, you kind of sand the material away. With plastics, you really dig in and take bigger bites. And so we have tooling, single flute tooling, that's set up to be able to do that. You know, the single flute tool is a 3mm torque tool. So that's 3 millimeters, and it will just, I mean, it'll have a rooster tail material flying off when it's bulk reducing. And then we jump down to a 2, and then a 1, and then a 0.6. We'll get the job done. I don't know if you need to go to a 0.3 unless you have something with real intricate areas to it, but that should get it done. And, you know, I would say in most mills, as long as they've been optimized with their tooling and strategies, for normal partial, you could be anywhere from an hour and 10 minutes to maybe 2 hours at the most for kind of a normal, unless it's a real big one, you might get over 2 hours, but that would be normal amount of milling time. And here's kind of what I was talking about with the rooster tail. You can see how that single flute, the biggest thing that you can do for milling these plastics is to get the material off and get it away, so it doesn't have a chance to heat up. And so that's what you can see here, is it's just throwing that material out of there and not letting it get gummed up on the tool, not causing a problem with the warpage of your appliance. So your options, right? So if you have acrylic teeth and acrylic base, right? Acrylic will bond to both of those. So you can use an acrylic as your intermediary material to bond it. There's also several companies out there that have a resin that's made to bond. You can also use some composites. Usually you have to use a bonder on each, a preparatory bonder on the sockets and the teeth, and then you can use an acrylic to fill that or composite. But that's fairly easy, right? Acrylic teeth to a printed denture base. That is usually you have to use like a resin built for that, right? So the acrylic, you're probably going to have to use a bonder, you know, like an intermediate priming resin or liquid to be able to bond to both, because they're two different materials kind of. There's a couple of materials coming out that I've been playing with that actually bond to acrylic pretty nicely, and they're a 3D printed material. There's a little bit of a bonder that you paint on, but acrylic bonds to it nice. So there's possibility for some of these materials coming along. I know there are some 3D printed materials where you just acrylics don't seem to stick to them at all. So that one's a little iffy because you're dealing with two different materials, acrylic and printed. Okay. Acrylic to flexible. So if you're going to have like a flexible nylon or a flexible polypropylene type base, you know, like a Bauplast or Duraflex type base material, now, you know, just about nothing will bond to those bases. I mean, some things will bond a little bit. There are some liquids that you can put on to kind of prime that material, but I think you still want to rely on some mechanical retention, right? So it's like reverse engineering. Whenever you inject a case, like a Bauplast or a Duraflex, you drill holes up in the teeth and you inject up in. So you're kind of reverse engineering it, make a socket, create some undercuts, some holes, some things to kind of lock that in. And then you could use a composite or an acrylic as long as it'll bond to the tooth that you've created. So you want to make sure you chemically bond to the tooth, whether it's printed or milled. And then in that socket, try to lock it in mechanically. So that's everything. I hope that gives you kind of a good, the big thing I was trying to get out of this is give you a good, well-rounded idea of, if you have a mill now, what you might be able to do in that mill to maybe keep it busier. If you're thinking of purchasing a mill, I want you to have confidence that you can keep that thing busy. And, you know, maybe if you guys are already doing that, maybe there was a few tips or hints in there that might make what you were doing a little easier. So I really appreciate your time. You know, Ian's gonna kind of talk a little bit about some of our some of the other parts to the milling and stuff, and he'll kind of finish things up. I appreciate you listening to me, and we'll answer some questions here in a little bit. Thank you.
Thank you, Kris, for sharing some valuable insight with us today. Now I'm going to turn it over to Ian O'Neill, Eastern Sales Manager for Roland DGA DG Shape Americas. Ian's going to tell us all about the DWX 52D Dry Series mills, as well as their denture capabilities. Ian?
Hello, everybody, and thank you, Lisa, for the introduction. I'm happy today to share the screen with a good friend of mine, Kris Schermerhorn. So, Kris, thank you for participating in this webinar with us. And my name is Ian O'Neill. I'm going to be talking to you today about the Roland DG Shape dental mills. So I'm going to take you through a quick overview of our offering and give you a better idea of what the capabilities of our devices are. So we're going to be covering the DWX52D and the DWX52DCI. Now, first we'll talk about the similarities of these machines, and in the next couple of slides we'll get into a little more of how they're different. All right, both machines are dry mills. They're both 5-axis and can mill the same types of materials. They share a material adapter system. So if you were to have one mill, the 52D, and then add on a DCI later on, both of those material adapter sets would be usable between both of your machines. Okay, one of the machines is a single puck device. The other one has the disc changer, which would give you the ultimate productivity workflow for your overnight milling, as well as continuous milling throughout your workday. Okay. So first, the DWX52D. Again, this is one of our dry mill offerings. It's a 5-axis mill, mills dry materials only. You'd be able to produce zirconia, PMMA, composite resin materials, PEEK, pectin, gypsum, should you choose to mill that, and fiber reinforced resins like a Trilor material. Okay. You'd also be able to mill block materials that are on a Cerec or universal type mandrel that would be a hybrid composite resin like a Vita anemic type material. This mill can also produce restorations out of chrome cobalt that would need to be sintered. So that would be the raw state before it goes into an argon furnace to be cured to become a solid state metal. Okay. This is a great machine for you to be able to start your first crown and bridge digital production. It's going to mill your zirconia crown and bridge work, full arches, anything like that. It would also be able to mill cases like Kris presented, your acetal, duracetal, or plastic type restorations, flexible partials, but you would lose the productivity that you would gain by having the disc changer on the machine itself. So with that, let's talk a little bit about the disc changer. The disc changer, again, these machines look very similar. The difference between the two is the addition of the disc changer. The machine can hold 6 discs at a time. You can open and close that chamber that holds the discs while the machine is milling. So you're constantly removing finished pucks and adding new ones that are needed to be milled, okay? So using a barcode scanner system, that changer would scan each one of those pucks, find the proper barcode for the mill job, transfer it over into the milling chamber, which you can see here in this image, and then go ahead and produce that workflow. Inside of the machine, we have 15 tool slots. That's going to give you slots for zirconia production, plastic production, or any of your specialty tools that we're seeing called upon in unique case situations, so things such as flat surfaces or screw access channels. Okay, so the idea behind the DCI is the production value. You load the machine up with jobs before you leave for the night. You come in the morning, you have a ton of work done. You remove all of those discs, begin to put them through your lab production, load the machine again, and cycle that machine through all day long. Much more productive. Again, both mills are 5-axis, very important for things like mill denture when we have undercuts or screw access channels. Both machines are driven by ball screw driven systems. Some of our older devices were a wire drive system, so this is much more accurate for undercut milling. We have intelligent tool control technology in each mill, which means you can have sister or backup tools for your mill. When one tool would expire from its tool life and it was placed back and there was a backup tool, the next time that machine needs that tool, it would pick up the new fresh tool. Both machines can be run from the same V panel. We want to think of the V panel as kind of your command center for your fleet of mills or your single mill. Each V panel can track up to 4 of our milling devices, and it would basically tell the mill when to start a job, stop a job, keep track of errors, milling tool life, and running calibrations, those sort of things. Our machine has an ionizer inside of it. If anybody has experienced milling plastic materials, there can be a static charge created from the suction unit to the milling chamber itself. All those plastic shavings, due to the static, can stick, making your cleaning process a little more labor intensive. So having the ionizer inside of the machine drops that static significantly. Most of those plastic particles are going to drop to the bottom of the machine and be evacuated out the back. A clean mill is a running mill. Okay. Air pressure. In some of our older mills, depending on the material type that you were milling, you would have to adjust the air pressure on the regulator. Now there is an automatic air pressure regulation that is adjusted based on the material file that's chosen and sent over to the mill. So less manual steps for the end user to do. So Kris talked a lot about flexible partial, and he even mentioned the TRK kit, which we do offer. Our TRK kit stands for Time Reduction Kit. And the idea behind our time reduction kit, for those of us who are not printing denture, it gives us the ability to pour our own true denture acrylic pucks on demand. So that can be varying in shades. Materials such as, let's use GC Nature Acryl, have 7 shades plus a clear. So you're going to be able to pour your own portable acrylic into a silicone mold, cure that in a pressure pot. When you polymerize that, you remove it. Now you have your true denture acrylic puck poured in-house. You send that to the mill. It's going to mill out the denture base in a separate puck, an aesthetic PMMA. You would mill out your teeth. And now you have a 2-piece digital denture. You're able to use that acrylic as a glue, loop them together, and take your final denture to polish. So the cost of pouring your own puck in-house is significantly less than purchasing a pre-manufactured puck. So you'd have to weigh out the cost of you doing the labor-intensive step of pouring your own puck, which is quite simple, or ordering one for 3 times the price as it would be to pour one. So very attractive solution here. The aesthetics are there, the strength is there, and the repairability is there. You're going to be able to reline and repair these just like it would be a traditional denture itself because it's made out of the same materials. Okay, this is everything included in that kit. And if you have more questions about that, we'd be happy to answer them. So one of the big questions we get is milling times for those mill dentures. A typical denture base is going to take us about 2.5 hours to mill, and that full arch of teeth would be about 1 hour and 40 minutes. So again, this workflow would be great for a machine like the DCI. When you leave work for the night, you load 4 denture-based pucks in, 2 PMMA pucks, and you start your mill. By the time you come in the next morning, you have sets of dentures ready to be cut from the puck, both teeth and bases ready to be luted together. So all of that work is done while no one's on site. Okay. Another option that we have is our DWX42W. DWX42W is our wet mill. It could be used in a lab or a practice that would be producing a lot of pressed glass ceramics. They want to go more digital. You know, they can design a single unit restoration very quickly, but they want to cut out the labor intensive steps of waxing, investing, burning out, you know, devesting, all of that. So you're able to produce glass ceramics or crown in a day type restorations in the DWX42W. 4-axis wet mill, again, needs that Serec universal mandrel. We have tooling options in this machine. We have high quality tools or a standard tool for a faster restoration. The machine holds 6 tools. You would use that same V panel we talked about with the dry mills, and the Millbox software, which is the CAM that runs the device, is included in the price of the mill itself. So turnkey solution. And a new feature inside of that 42W is our AK1 kit. Now you're able to produce your own custom abutments in-house for anything that you would need to produce. So instead of outsourcing, waiting many days for those to come back, you're designing in your design software, milling it in about 1 hour, you have your custom abutment right there in-house. Okay. The AK1 kit comes with everything you need to get started outside of those titanium blanks itself. We do partner with DES, NT Trading, Medentica, and Geomedi. So you would have the choice of who you'd be working with or what brand of titanium blank you'd be purchasing. We're also going to give you a set of tools, a receptacle tray, a torque driver, and a mesh filter to make sure all those titanium shavings don't get inside of your cooling tank. Okay. So that's a brief overview of our milling solutions. And in the question and answer segment, we'd be happy to field any more questions you have about our milling devices. And thanks for joining us, everybody.